Good morning, everyone. Welcome to a lecture on scalars and vectors, part one. In this lecture, I'm using the slides that can be found in www.slideshare.net, and this is authored by Khan, Khan Saif. Those slides have no voiceover, so in this particular lecture, I'll be putting a voiceover to that slide, but you can visit that site and get some other slides which may be of interest to you. So let's start with the lecture. So this is scalars and vectors. So there are two quantities. Um, we we have a scalar physical quantity and a vector physical quantity, and we start with the scalar quantity. What is a scalar? So length is a physical quantity that is a scalar. Um, it doesn't have uh, any direction. You can measure a length of a table. You can measure a length of a car. For example, in this case, you have a car that is 4.5 meters long. So that's the magnitude of the length. And you also have a physical quantity called mass. In this case, you have a mass of gold, which is 1 kilogram. And then you also have time, which is, in this case, you have 12.76 seconds as being shown in the stopwatch in the figure. And temperature is also a scalar quantity, and you have here 36.8 degrees Celsius, a normal temperature of the body. So some of the scalar physical quantities are mass, length, and time. Mass, length, and time are fundamental quantities. All other quantities in the that's used in physics are derived, or even chemistry or in science, are derived from mass, length, and time. Mass in kilograms, length in meters, and time in seconds. That's for the uh, international system of units. For other system of units, you also have different dimension. Like for the mass, they use pound, they use feet for length, and they use seconds for time. Other scalar quantities are temperature, volume, density. These are pure numbers with units. So a quantity is only significant is also if it has a unit. Say for example 5 meters. If you just say 5, then it's just 5, it's meaningless. But if you say 5 meters, then you will know that the 5 meters is a length, and you know how to measure 5 meters. That's 5 times 1 meter sticks. Now, what is a vector? A vector is another physical quantity, but this time one ingredient added to the number is the direction. So in this case, you have position. Position is determined by distance and the direction where it's located. So here in this particular slide, you have position of California from North Carolina is 3,600 kilometers to the west. So you can determine the position of California from North Carolina by measuring the distance and uh, putting in the direction of that distance. So another vector quantity is called displacement. So here, displacement is when an object moves from one point to another. So you have, for example, a plane flying to a plane flying from United States flying to China. In this case, you have a displacement. It's a straight line distance that's traveled by an object from one point to another. So you have the displacement from United States to China by the plane. So the displacement is 11,600 kilometers to the east. So a direction is specified. A vector again has a magnitude and unit and a direction. Most importantly, a direction. So example of that are position, displacement, velocity. Velocity is like speed with direction. So you have to specify the direction because you want to know where an object is moving towards. Say for example, 5 or 50 meters to the north, or 50 meters towards you, or 50 meters going west, for example. That's different. Those are different physical quantities. Those are different velocities because they have different directions. Acceleration also, momentum, and force are example of these physical quantities called vectors. So we can represent a vector by an arrow where you have here a tail that's represented by the dot and the arrowhead here. The tail is the origin of the vector and the arrowhead is the endpoint of the vector. So it tells you where the object came from in the case of displacement, and where it's heading or where its final destination or final position is. The length of the arrow is the magnitude. So if you have this length representing 3, then this vector would be representing a vector with magnitude greater than 3 because it's the arrow. And the theta here is the direction. In that case, you can say that the vector AB, this is the notation of a vector. You have some symbols here and you have an arrow above it. That's a vector. So in this case, you have vector AB is theta degrees above the x-axis, or theta degrees north of east. Or you can say the direction of here is theta degrees north of east, or theta degrees above positive x-axis. You can say that. Now let's go to some representation of a vector here. You have vector A. This has the direction going. The direction of the vector here is north of east. The direction here is, or you can also say this vector is on east of north. So depending on the angle. So for example, this is 15 degrees. For example, this is 15 degrees north of east, or 75 degrees east of north. So if you have here, like this is 20 degrees for B, so B is 20 degrees south of west, or 70 degrees west of south. So you can say that. Or this is also 20 degrees below negative x axis. You can also say that. For P, you have this vector. So say you have alpha, angle alpha. So this is alpha below, alpha degrees below positive x axis, or alpha south of east, alpha degrees south of east. Or this is, you can say that 90 degrees minus alpha east of south. You can also say that. So those are equivalent directions. So some vectors, by the way, some vectors are represented by capital letter with arrow above. So here you have A, B, and P. So if you're representing a vector A, then you cannot represent another vector in the same scenario, another vector A with a different direction. So you have to really name it with another letter. So here you can also usually in physics you are going to use vectors repetitively. And some of these vector quantities are position. For example, Here R, and you have V and F. Your R is usually for position, V arrow is for velocity, and F is for the force. There are types of there are two types of vectors depending on the orientation. One is called uh, parallel vectors, and these vectors have the same direction, but they may have different magnitude and units in magnitude. So for example, you have A and B. So if they're heading the same direction as in this one, um, northeast, for example, A is going northeast, B is going northeast, it's the same angle with the x-axis. So they are parallel vectors. P and Q are also parallel vectors because they have the same direction. And they're also equal vectors. They're parallel with the same magnitude. Say, for example, A and B are equal, the same magnitude and unit. So A is equal to B. That's how you define equality. They have the same direction and the same magnitude and units. In this case, P and Q are also equal. There's also antiparallel. This is the second type. Two vectors which have exactly opposite directions are called antiparallel vectors. Here you have this. A and B are antiparallel. P and Q are also antiparallel because they have opposite direction. In two antiparallel vectors can be negative of each other. So A, in this case, A is negative of B because B is in this direction and A is in the opposite direction. So A, or you can also say that B is negative of A. That's also the same. It's the same thing. And here you can also say that P is negative of Q for this case. So it just means that the magnitude and unit are the same, but the directions are exactly opposite of each other. There are collinear vectors. Collinear vectors are two vectors that are said to be acting on the same line. So, for example, you have A and B here. They're heading towards each other. So, in the game of tug of war, in tug of war, you're pulling a string or you're pulling a rope, and that rope is experiencing tension going to the left and going to the right. In that case, the forces are going away from each other. So you are putting both parties or both groups are putting force on a rope that are that are acting on the same line. So you are uh, putting collinear forces or vectors in the rope. So in this case, A and B are heading towards each other. It's like you're pressing a ball. You and your friend are pressing a ball or pushing a ball towards each other simultaneously. On the other side, P and Q, they are also acting on the same line. However, they are on the same direction. So this means that a person, like if you're putting a force on a rope. If you're pulling something, you, you are pulling up the rope, and the other person also pulling the rope with you, then you have um, forces acting on the same direction. Here, there are four vectors A, B, C, and D, and these vectors are called co-initial vectors, meaning they come from the same initial point. So, say for example, A, uh, they come from this point. So, for example, one is, this is an object, this is a tree, for example, and a person A is pulling the tree on that direction, and person B is pulling the tree in another direction. C is pulling the tree to the east, for example, and D is pulling it to the southwest. So those are co-initial vectors. They come from common initial point. Then you also have coterminous vectors. They end on the same point. So here A, B, and C, they end on the same point here. Coterminous. And then you have coplanar vectors. You have vectors on the same surface, the same plane. Say for example, we have A, B, and C and D here. They're located in the same plane. Like for example, in a surface tension experiment, you have a bubble that's plain bubble on a plane surface, for example. The forces on the thin film of bubble, they are acting on the same plane, and they have different directions, and the direction is actually radial in direction. So it's coming from the center to the edge, or from the edge towards the center. So they are in different directions, so they are coplanar. Those are the forces on surface tension. And you also have vectors distributed over space. So in this case, you have A, B, C, and D. They are in different directions, but they are not in the same plane. So A is in this direction, A is in this direction, in that direction. B is on another direction, and C is on another direction. So they are different in direction. They're distributed over space. There are also vectors called polar vectors. That means that um, the vectors usually does not um, does not change direction from point to point, in a say, or maybe this is these vectors are they have straight line effects. They don't change direction from point to point, like electric field, which you will learn later on. Electric field or magnetic field, these vectors are the first that you will learn in mechanics: displacement, velocity, acceleration, and force. Those are examples of polar vectors, straight line vectors. But there's also axial vectors. Say for example, if you have a rotating planet, say the Earth, it has an angular momentum, and the angular momentum is determined by your right hand. So if it's rotating counterclockwise using your right hand, the vector is perpendicular to the plane of rotation. So use your right hand in determining the direction of the axial vectors. Some of these vectors are angular momentum, angular velocity, angular acceleration, and torque. We can add vectors, and this is not ordinary addition, because when you say ordinary addition, that's what we call algebraic addition. So when you say 5 plus 3, algebraically that is 8, or 8 minus 10, that's negative 2 algebraically. But for vectors, what you do is you have to draw the vectors, and then you connect the origin of the first vector to the head, or to the destination of the final vector. So say for example, you come from Egypt, you go to Yemen, and then from Yemen to Iran. Your final displacement will be from Egypt, and final is Iran. So this is your vector that represents it. C. So in this case, you're adding vectors A plus B is equal to C. And look at this. The magnitude of C is almost the same as magnitude of A and magnitude of B. They're forming it's more or less an an equilateral triangle. So it doesn't mean, like for example, in ordinary algebra you say 5 plus 5 is equal to 10. So in this case, for vectors, when you add a magnitude of 5 plus a magnitude of 5, you can still result in a magnitude of 5. This one, for example, is 5, 5, and this can also be 5, but in other direction. Of course, A has a different direction with B, and B and A have the same different direction as C. So you have also parallelogram method. Here you have, let me just describe you here. A box is being lifted by two pulleys, and you have here a box that is pulled by this rope, and the tension in the rope is A, and on the other side the tension is also A. Of course, because this is a continuous rope, so the tension should be the same if the pulley is frictionless. So when it experiences no friction, the tension in the rope would be constant. So this is A, and this is supposed to be A. So if this is pulled by another person and pulled by tension B, then this is also tension B. So how do you add them? So this is A, and this is B. That is the direction by which the box is being pulled. So you can add this by connecting A. You have A here, and then you have B. You can connect the tail of B to A here. So your C, your sum is here going up. Or you can also do the other way around. It's the same thing. You have B here, and then you connect A to here, and then you have the C also. So it's the same thing. And then that is actually called a polygon method, and this is another example of polygon method. So you have four vectors acting on the same point. These are co-initial vectors. So you have a, this one, you have a here, and then you have b here, you have b, and then you have c, and then you have d in this direction. So you connect the tail of the first to the head of the last. So this is now your resultant. So this is your E. That's the resultant of the four vectors. And by the way, the addition of vector is a commutative operation. That means that you can, as I've said earlier, in this case, when you add A and B, is the same as adding B and C in a different order. B and A in different order. So in this case, you have A added to B, then you have a C. This is the resultant, and this one is also the same thing, C. Associative property, you have A, B, and C. You have A, B added first, or you can also add B and C first. So you have this vector, then you can add A to this, and then you have the same result, the same resultant vector. Here you have AB, and then you add to C, so that's also the same vector D. Subtraction of vectors. Here you have an addition of vectors, A added to B, and you result to this vector C. And here you have A minus B. So you have A here. What is negative of B? Negative of B would be this vector. So if you add the negative of B to A, so that would be here. So this is negative B. So if you add them, A plus negative B would be the resultant would be this one. So your vector would be, so you should look like this one. So A minus B is the same thing as A plus negative of B. We can also add the vectors analytically. Here we have, if we look at these two vectors, we have P and Q, for example. We add vector P and Q. So in this case, you have the resultant P and Q here, but when you add by tip to tail method, this is Q, and then you have a final resultant vector there, which is R. So in this case, you have OC as the resultant vector, and OM here, OM forms a right triangle with OC together with CM. So they are right triangle. So by Pythagorean theorem, OC square is equal to OM square plus CM square. And then OC is also equal to OA plus AM square. plus cm square. So when you expand this is OA square plus 2 times OA times AM plus AM square plus CM square. And OA square plus 2 OA times AM plus AC, this is AM uh, AM, this is AM and CM, right? So AC is what? This is AM square plus CM square is equal to AC square by Pythagorean theorem, because they also form right triangle. And that this one's here becomes AC square. So in this triangle, you have cosine theta is equal to AM over AC. AM over AC, this is AM over AC, and then you will have AM is equal to AC cosine square, and OC square is equal to OA OA square plus so here is OC, but you have, now you can write AM here, and of course in terms of AC, so you can write that as AC cosine theta. So you can now, what is OC, by the way? OC is R, and P is OA. OA is P, and you have OA, this is 2P times AM is AC cosine theta, but AC is Q, so this is Q cosine theta plus Q square. So finally you will have R equals the square root of P squared plus 2P Q cosine theta plus Q square. So that's it. This is now the magnitude of the resultant, this one here. So you can get the magnitude of P, the magnitude of Q, you add the squares, and then you also add 2PQ times cosine theta. So what is the direction of the resultant? The direction of the resultant would be would be this angle alpha, for example. So what is that? That is alpha degrees north of east, or 90 minus alpha degrees east of north, or alpha degrees above the positive x-axis. That's the same. So how would you determine that? So in the triangle CAM, 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 you have sine theta is equal to CM over AC, and cosine theta is equal to AM over AC. So you have this relationship from here, and then OCM, OCM is tangent CM, tangent alpha CM over OM. CM is this one, and then AM is this one. OM is equal to OA plus AM. So tangent alpha would be this one. This is now the direction. How do you get alpha? Alpha is just the inverse tangent of Q sine theta divided by P plus Q cosine theta. So that's the end of the part 1 of scalars and vectors. We will continue with part 2.